Hello everyone, welcome to Recitation session week 14 for CEE222 Water Resources Engineering. This week we will have 4 different questions and we will get started with 11.4.1 in your textbooks. So first let me get started with the question text. Here we need to determine the time of concentration for the runoff from a concrete parking lot. The overland flow segment is 25 meter long with a slope of 0.5%. Then this overland flow segment moves water into a shallow V channel and it drops 2 meters in elevation over 100 meters in length. So we have length of shallow water channel which is 100 meters. Finally, the stormwater is picked up in a 400 meter long 2 meter wide rectangular channel flowing 0.5 meter deep. So this is our rectangular channel at the end of this flow. The concrete channel has a slope of 1% and we need to determine the time of concentration in minutes. The 2-year and 24-hour rainfall depth is 4 cm. And finally, we need to determine what percent of time of concentration is attributed to this 25 meter long overland flow. So let me summarize the question. So we need to find the time of concentration, and when we say time of concentration, it means the distance from the most distant point in this watershed. This is a demonstration of watershed. And when we say time of concentration, it is a distance from, let's say, the most remote, most distant point to the outlet. So here we have outlet. So basically we will find the distance from here to here. And to find that, we will have 3 different flows throughout this watershed. So the first one is overland flow, which was given here. So after that, this overland flow is flowing into the shallow V channel. So in this channel, we will have shallow concentrated flow. And after that, this stormwater is picked up by the open channel flow here, which is highlighted by orange. So this open channel flow will move water from this point to the outlet. Therefore, we will have these 3 different flows. And finally, we will see the open channel flow properties. It is a rectangular channel and it has a slope of 1% and its length is 400 meters. And it's 2 meter wide and 0.5 meters deep. So let's get started. What we are going to do is we will calculate time of for each flow type, and at the end we are going to sum all of these and we will obtain the time of concentration. So let's get started with sheet or overland flow. And actually let me write that. When we say sheet flow, it is usually overland flow. So from equation 11.12, you will see the equation for sheet flow segment. So it is the travel time flow. And let's continue what we have. So this is coming from the equation, so it is 0.091 times, since we have a concrete parking lot, you can get the Manning's roughness value, which is n. So it is 0.011 from the table in your textbook. And the length is given as 25. So we have 0.8 here. So here P is the precipitation. And let's say 40 millimeters because it was given as 4 centimeters. Precipitation. And then we have the slope for the sheet flow, which is 0.5%, and it is this one. So from here, the time for the overland flow, the travel time, will be 0.043 hours. So this is the first travel time, which is the first segment, which is overland flow. And now we are going to skip to the next one. Let me use another color. So right now we are doing it for shallow concentrated flow. The travel time for this type of flow is, let me write travel time to, it is length over velocity. And also if you check your textbook, you will see equation 11.14. This is the velocity for paved surfaces. So since we had a parking lot, we assume that it is paired, so we will continue with that. And the velocity is 0.19 times slope to the power of 0.5. So this is going to give this is because we had 2 meter of drop in the elevation, so it is 0.2. And this gives 2.77 meter per second velocity in this shallow concentrated flow. So to find the travel time, the length is 100 meters and we have 2.77 meter per second. And of course we need to find this in hours, then we will convert it to minutes. So let's say this is meter and we will convert it to hours. So we have 1 hour over 3600 seconds, and this gives 0.01 hours. Okay, so we calculated the travel time for this shallow concentrated flow, and we already calculated the travel time for overland flow. And finally we need to find open channel flow travel time. So actually this is coming from 2 meter over 100 meter, because in the equation it says dropping 2 meter in elevation over 100 meters in length. So this is giving the water course slope. Okay, finally let's focus on the open channel flow. So it is actually very similar to what we did in previous weeks, because this is also an open channel flow. So we will apply Manning's equation. So also for the open channel flow, the travel time is length over velocity, and we know the length but we don't know the velocity. Therefore we are going to use Manning's equation for velocity. So the velocity will be equal hydraulic radius, we have slope, so since this is open channel flow, we can get this n value from the table in your textbook. So it is 0.013, and the hydraulic radius is, if you remember, area over perimeter. So here we have 1 square meter, and we have a perimeter as 3 meters. So we have hydraulic radius as 0.333, and the slope is given as 1% in the question, so we can directly write 0.01. And from here the velocity is 2.96 meters per second. So the travel time, the length is 400 meters, and the velocity is 2.96. And if you convert it to hours, we can get 0.03 hours. So with that calculation, we calculated all of the travel times for 3 types of flows. So the total time of concentration, we have 0.043, which is in this overland flow. We have 0.01, and we have 0.03. Which gives us 0.083 hours, which is equal to 50 minutes. So from this point, which is the distant point in this watershed, to the outlet, it takes 5 minutes, not 50. It takes 5 minutes from here to this outlet. Now, also in the question it says what percent of time of concentration is attributed to the 25 meter of overland flow, which is here. So let's do that calculation. So to find that, we will just use the time of travel time for overland flow over the total time of concentration, and this gives, we cannot see that, this gives 0.52, which is 52%. Okay, let's continue with second question, which is 11.4.2. So this question is actually very similar to the first one. We are just using British units. So this time we will be using different equations, but the remaining calculations will be almost same. So let me get started with the question text. The hydraulic length or longest flow path for a watershed is 2,800 feet. Along this path run of initial travels over the land surface, which is overland flow, and it drops 3 feet in elevation over 100 feet. So this is actually 150. So this means we have a slope in this sheet flow or overland flow 3 over 150. And the type of the surface is short grass, and then it moves into shallow concentrated flow for a distance of 450 feet with an average velocity of 2 feet per second. The remainder of the travel path is a through pipe, so The diameter for the pipe is 2 feet. And it is flowing half full on a slope of 1%. So again, we need to determine the time concentration in minutes. And the 2-year and 24-hour rainfall depth is 3.4 inch. And finally, we need to determine what percent of the time of concentration is attributed to this overland flow. So let's get started with overland flow. So since we are using British units, the equation will be changed. So the travel time is 0.007 Manning's m value times length to the power of 0.8. And we are going to divide it by square root of the precipitation times slope. So let's see what we know. So we have this constant value, and we are using Manning's m value as 0.15 because it is short grass. We have length 150 feet. The precipitation was 3.4 inches. And we have slope, which is 3 over 150, which gives 0.02. And from here, we get 0.219 hours. So this is the travel time for the overland flow. So let's look at shallow concentrated flow. Again, the travel time is length over velocity. And this time we already know the velocity, which is 2 feet per second. And the length is 450 feet. And let's convert it to hours. So from here we will get 0.063 hours. And finally, after this flow, we will have open channel flow, and it is actually a pipe, so that we need to use equations for circular shape. So let me write channel flow, and it is actually pipe, or let me say half full pipe. So since this is not completely full, it is not pressurized, so we will use Manning's values, Manning's equation again. So velocity will be equal to 1.49, and Manning value is 0.013. This is also from the table. We have hydraulic radius, and hydraulic radius for the circular shapes, d over 4. D here is diameter, and we have 2 feet over 4. So this is actually 0.5. And finally we have slope, which was given as 1%. From here, we will get the velocity as 7.22 feet per second. And now we can calculate the travel time using the same equation here. And also in the equation, it says the total path, which is the total flow path is 2,800 feet. Use that. It is 2,800 feet. And we had 150 feet here, 450 feet here. So the remaining is 2,200 feet. So let me write travel time for open channel flow. The length will be the remaining part, which is 2,200 feet. We have 7.22. And again, we have 1 hour over 3,600 seconds. And this gives 0.085 hours. So here we have 2,200 and we have 7.22 feet per second. So from here we can calculate the total time of concentration. So let me write it here. So we have 0.219. We have 0.063. And finally we have 0.085. And this gives us 0.367 hours, which is actually 22 minutes. And we need to find the percent of the time due to overland flow. So for the overland flow, we have 0.219 over the total. And this gives 60%. So 60% of this total time of concentration is attributed to the overland flow. Now we are at question 3, 7.2.2. A comment is made in the paragraph which follows equation 7.14, suggesting the selection of the radius of influence can be somewhat arbitrary, which means the discharge is not overly sensitive to this variable. Suppose the radius of influence for a 20 centimeters diameter well is approximately 250 meters plus or minus 50 meters. So we need to determine the percent error in discharge that results from this 20% change. We will assume a 50 meter thick unconfined aquifer, which has a constant the drawdown at the well of 3 meters. So first, let's draw what we have. So we know that the thickness is 50 meters. So here HO is 50 meters. And we also have a drawdown, which is 3 meters. So here we will have HW, which is the height at the well. So it will be 50 minus 3, 47 meters. And the radius of the well is 0.1 meters. So we had 20 centimeters diameter, and we convert it to meter and find the radius one. So we need to apply equation 7.14, which says that the flow rate is, the discharge is equal to pi times k HO minus HO square minus HW square over ln radius of influence over radius of well. So let's write first what we have. So we know that we can obtain K from the table. We know that HO is 50 and HW is 47. So let me write all of this. So first, let me write it for right here for the first change. So let's say we are dealing with minus 50 meters of 250. So this means that we have a radius of influence as 250 meters, and we need to see the change in discharge for radius of influence 1 and radius of influence 2. So let's say this is 200 meters and this is 200 meters, because in the question it says it can be plus or minus 50 meters. So that we can see the change in discharge. So for 200 meters radius of influence, we will have pi, and we can get a value from table 7.2. And there's a range. It is between 10 to the power of minus 4 and 10 to the power of minus 2. So we can get 10 to the power of minus 3 times we have 50 square over 47 square. Sorry, to the power of, over ln 200, which is radius of influence, over radius of well, which is 0.1. Similarly, we are going to do the same for radius of influence of 300 meters. So again, we have pi, we have 1 times 10 to the power of minus 3 for the k value. We have 50 square minus 47 square over ln, and this time we will have 300 over 0.1. And this gives, the first one gives 0.12 cubic meter per second, and this one gives 0.114 cubic meter per second. So we need to find the change in discharge, and we need to find the percentage error in discharge. So the discharge, if the radius of influence is 200 meters, we will get 0.12 plus 0.114. So they are just taking the average of these two discharges. So it will give 0.117 cubic meter per second. You can also use this equation to find the discharge at 200 meters radius of influence. So it will also give the same one. So you can use either way. And to find the change in error. For example, if we take 250 value as reference and if we deal with 200, so let's say by doing that, we can see the change in the discharge when we take this value as reference. And so this is going to be 250. Excellent. Okay. So we have 0.12 minus 0.117 over 0.117, and it gives 0.26, and this is equal to 2.6% change in the discharge. And you can also do that if you want to use value of 300. It will also give 2.6%. Okay, now we are at the final question, which is 7.2.6. Here, a 40 centimeters diameter well draws water from a 30.5 deep unconfined aquifer at the rate of 0.0151 cubic meter per second. The drawdown at an observation well 50 meters away is 1.5 meters, and the drawdown at the well is 6.5 meters. So we need to determine the radius of influence at the well. So it is RO. And also determine the drawdown at a distance of 100 meters from the well. Similar to the previous question, let me draw some information. So first of all, we have a 30.5 meter deep unconfined aquifer. We have 30.5. And we have an observation well 50 meters away. So let's say we have an observation well and the length is 50 meters. I mean, the distance is 50 meters. And it says we have a drawdown, which is 1.5 meters. So from here, we will have 1.5 meters. Therefore, we will have a distance from that point, it will be 29, because we had 30.5 meters here, and we have 1.5, which makes this distance as 29 meters. Also in the question, it says we have drawdown at the well is 6.5 meters. So let's say we have 6.5, which makes this area 24 meters. Okay, now we can continue with equations. So in this question, we don't know K, so that we need to do a back calculation and obtain K. And after that, using that K, we are going to use the same equation and we will get the radius of influence. So we will use equation 7.16. it is H square is equal to HOB square minus Q by K ln radius of influence over value radius. So first of all, the H is calculated as 24 meters, which comes from here. Actually, let me correct this drawing. So here's the drawdown is 6.5 meters, and we have 24 meters. So 24 is equal to HOB. It is the distance between, sorry, it is the head at the observation well. So since we had drawdown, the value was 29. Cash minus Q. It is given as 0.151 over pi, and we do not know K. And this time we are using 50 meter as radius of influence because we actually need to find K. So this radius of influence is not the actual value, but we are using it to find K. So which is the distance from the well for the observation. And we have 0.2, which is coming from here, 40 centimeters diameter. For the radius is 0.2 meters. So the only unknown here is K. So we can calculate it as 0.0001 meter per second. And here K is permeability. And you can find the table in your textbook. So now we are going to use the same equation. This time we know the K value, and we are going to get radius of influence. And this time we are still using 24 as the H because it is the head at the pump well, so it will be kept constant. But this time the depth for at the observed well will be 30.5 meters, which is undisturbed depth. Because we need to find the true radius of influence, and therefore we will assume a zero drawdown at the observation well. So minus 0.01 over pi times 0.001, which is K, times ln, so radius of influence over radius of the well. So from here we will get radius of influence as 318 meters. So this answers the first question, which says determine the radius of influence of the well. And now we need to determine the drawdown at a distance of 100 meters from the well. So this time we need to find this value so that we can end up with the value of radius, drawdown. So we have 24 minus 0.0150. We have pi, we have k as 0.0001. And then radius of influence. So the question says it will be 100 meters. So let's say this is 100 over the radius, which was 0.2. So basically here, what we did is the question wants us to find the drawdown at a distance of 100 meters. So at the beginning, we have 50 meters distance, and right now we want to find at 100 meters. And we calculated this radius of influence based on these values. Now we need to assign 100 for the radius of influence, and we will do back calculations to get this value, which is the depth at observation well, depth for the observation well. So here, HOB will be equal to 9.6 meters. So drawdown will be, so we had depth as 30.5. So it should be 30.5 minus 29.6 meters, which is 0.9 meters.